Okay, so this is going to be 3.4, solving exponential and log equations. Maybe have an application at the end. Let's take a look. So first we're going to begin with the exponential equations. Log equations. There's two methods we'll use for solving these and for solving the exponential equations. The first method is following from the one-to-one property. So a function just to the side here, if f of x1 is equal to f of x2, then x1 is equal to x2. So this is a property that one-to-one functions have. And we'll use this property to solve exponential equations and logarithmic equations. In terms of our exponential equations, this definition will look like the following. If you have b to the x1 equaling b to the x2, then x1 has to equal x2. Okay, so let's look at number 2. And these help you evaluate logs. If you had trouble with logs after you go through these homework exercises, it should be a lot easier, because this is really just asking the log base 3 of 81 is equal to what? Okay, so let's see, 3 to the x, and what we want to do on the right-hand side is to rewrite it with base 3. Okay? So 81, basically you're asking to what power? 3 to what power is 81? So 3 times 3 is 9, times 3 is 27, times 3 is 81, so 4. So x is equal to 4. Let's look at number 6. We have 3 to the 2x plus 1 equals 27. And again, you want to get the same base on both sides and then equate the exponents. So you'll have 3 to the 2x plus 1 equals 3 times 3 is 9 times 3 is 27. Right? And then we can equate the exponents. 2x plus 1 is 3. And then solve for x. So we get 2x equals 2, and then x is equal to 1. Okay, let's look at 12. So you have 125x equals 625. In this case, neither seems to be the base sort of that we need to get both in terms of. So over here, we didn't have to do anything to the left-hand side, but in this case, we're going to have to. So 125 is the same as 5 cubed. 625 is the same as 5 to the 4th. Okay. And to equate the bases, we have to use our exponent rule. So remember, if you have a to the x raised to the y, that's the same as a to the x times y. So over here, you have 5 to the 3x, and then equals 5 to the 4th. So finally, you can say 3x is equal to 4. So x is equal to 4/3. More. Number 16, 7 to the x minus 2 over 6 equals the square root of 7. So hopefully by now you've gotten into the habit of rewriting these root symbols as exponents. So let's do that. And then we can extract the exponents. So you get x minus 2 over 6 equals 1/2. If you'd like, you can cross multiply. So you get 2 times x minus 2 equals 6 times 1. So distribute 2x minus 4 equals 6, and then 2x equals 10, and then x is 5. Let's look at 22. We got e to the x plus 4 equals 1 all over e to the 2x. And so again, you're trying to get these bases. So this time, the exponent rule we're kind of going to need is the negative exponent rule. So if you have 1 all over a to the x, you can rewrite that as a to the negative x. Okay. So I can rewrite e to the x plus 4 as e to the x plus 4. Sorry, I'm rewriting the right-hand side. E to the 1 over e to the 2x is e to the negative 2x. And then you can equate the exponents. X plus 4 is negative 2x, and then get the x by itself. So you can add the 2x over here, so you get 3x. Over here is negative 4. Finally, x is negative 4/3. Okay, so that's the first method for solving exponentials, the one-to-one method. The second method then is to just simply take the log of both sides of the equation. So section 2, I suppose, using logs to solve exponential, I'll just write expo equations. Okay, so 24. We have 10 to the x equals 8.07. And you see, hey, I'm not going to be able to do this in my head, I don't know what number that x should be. I can't find a common base, so I need a different method. So that method is to use the log, and in this case, I'll use the common log because I want to use the log that has the same base as the base in this exponential expression. The base here is 10, so I want to use log base 10. Okay, so log base 10 of 10 to the x is equal to log base 10 of 8.07. And of course, for the common logs, we don't really write base 10, right? So it's just log of 10 to the x, log of 8.07. Then, because of the cancellation equations, log base 10 of 10 to the x is just equal to x. And then on the other side, you have to use your calculator to evaluate that. Log of 8.07. So x is approximately 0.91. Here I have in 26, e to the x equals 0.83. It turns out we use the natural base e so much that in general, when you take logs on both sides, you're probably going to be using the common log. Okay? And it's especially true because your calculator is more, it seems like my calculator doesn't even have a log base 10 button. It just has the natural log. So you can always use the same log regardless of the base. Like back here, I was saying use log base 10 because the base of this is 10. Here, use log base e because the base is z. But in general, you can always use the same logarithm. So if you want to, you can always use the natural log, which is what you'll do if you keep taking math and you take it in calculus. Anyways, over here, because of the cancellation equations, log base e of e to the x is just x. And then over here, you get ln of 0.83, and then you have to run to your calculator and get an answer. Okay, let's look at 32. And in this guy, you need to isolate the exponential term before you can go crazy with your logarithms. Okay, so in particular, I need to first take care to isolate this thing right here. Okay. So this is a common theme throughout this course, isolating something like when we did the absolute value inequalities or absolute values. So we have to isolate the absolute value. When you did radical equations, you want to isolate the radical. So here, when we do exponential equations, you want to isolate the exponential. So we'll divide both sides by 4. We'll have e to the 7x equals 10273 all over 4. And then you can take the natural log on both sides. So ln of e to the 7x equals 10273 ln, excuse me, 10273 all over 4. This time you're not going to get just plain old x. You get 7x instead. If you prefer, you can think of it as literally doing a power rule. So you'd have 7x ln of e equals ln of 10273 all over 4. And then the ln of e, of course, is log base e of e. And e to what power is e? Well, that's just 1. Okay, so this thing right here is just the same thing as 1. So you can rewrite it as 7x times 1, but at the end of the day, it's just 7x. And then you're going to divide both sides by 7. Okay. Plop it into your calculator and get an approximation. I got 1.12. Okay. Okay, let's look at another one. We get 36. E to the 4x minus 5 minus 7 equals 11243. And again, you need to isolate. You need to isolate this thing before you can do natural logs on it. So I'm going to add 7 to both sides. You get e to the 4x minus 5 is 11250. And now you can do your natural log. So ln of e to the 4x minus 5 equals ln of 11250. Over here, the ln and the e kind of cancel out. So you get 4x minus 5 equals ln of 11250. Then you're going to add 5 to the other side. So what are we doing? We're isolating again. Ln of 11250 plus 5. And finally, divide both sides by 4. So you get x equals ln of 11250 plus 5 all over 4. Okay. Plop it into your calculator. I got approximately 3.58. Okay. So 2 more and then we'll move on to logs. So 42. We have 7 to the 2x plus 1 equals 3 to the x plus 2. Okay. And I'm fond of putting this one on the test. Let's take a look. So ln of 7 to the 2x plus 1 equals ln of 3 to the x plus 2. And in this case, there's no way to get the logs to kind of cancel out. The cancellation equations won't apply because you can't get the same base on both sides. Okay, so you're going to sort of be stuck with this ln7 and this ln3. Do the power rule, you bring down the 2x plus 1, and then you have times ln7. Over here, power rule, bring down the x plus 2, and you have times the ln3. And then you have to solve for x. So it's a matter of distributing the ln7. So you get 2x ln7 plus ln7. Over here, you have to distribute the ln3. So x ln3 plus 2 ln3. Then you want to get all the x terms on one side. So I need to get this guy and this guy on one side. Okay, so I'll just subtract 2x ln7 minus x ln3. The other side, you got 2 ln3 minus ln7. Now you can factor the x out of this side, and you get x times 2 ln7 minus ln3 equals 2 ln3 minus ln7. I'll move up here. Divide both sides by this 2 ln7 minus ln3. And you get x equals 2 ln3 minus ln7 all over 2 ln7 minus ln3. Okay. You can condense this. I don't recommend it, but you can, especially if you're trying to put it in your calculator. This will be ln of if you bring in the 2, it'll be 3 squared, so 9 minus ln 7. And then downstairs, if you bring down the 2, it'll be ln 49 minus ln 3. And then you could rewrite that as ln of 9/7 all over ln of 49/3. And then there's nothing else you could really do at that point except put it in your calculator and hope for the best, approximating at 0.09. Okay, the next one's a little different, and it's a quadratic form. Okay, so 43e to the 2x minus 3e to the x plus 2 equals 0. So you see it kind of has that form, x squared minus 3x plus 2 equals 0. And so you may be tempted to factor it, and you would be right. That's what you want to do. So e to the x times e to the x. Because remember, if we refoiled e to the x times e to the x, when we get our first term, you add the exponent, so that'd be e to the 2x. Right, so then it's minus minus. It will have 2 and 1. So then we have e to the x minus 2 is 0, and e to the x minus 1 is 0. Now to solve each equation, so I have e to the x equals 2. Over here, e to the x is 1. And you have then do ln on both sides. Ln of e to the x is 2. So x ln e is 2. Then over here, ln of e to the x is 1. So you have x ln of e is 1. And then the ln of e, of course, is just 1. So you have x is 2. Or you can just go straight to the cancellation equations. This x is 2. Here, x is 1. Okay, so that's really the tall and short of it all for exponential equations. Okay. Now we want to move on to logarithmic equations, and sadly, now you're going to have to check your solutions. Okay. It's because some of the properties you'll use in solving logarithmic equations can introduce things that aren't really solutions. Okay. So you're going to have to check your answers, and I need to see the proof of that. Okay, you can't just say you did it in your head. I want to see the check. I've been burned too many times by students, so please show your check. Let's take a look. Log equations. Please check your solutions. Okie dokie. So there's going to, again, be two methods for log equations. The one-to-one property will give us one method, and then the other method will just use the definition of the log. So first off, we're going to take a look at the definition. And so if we have if log base b of m equals c, we can conclude, or rather turn it into an exponential equation, say b to the c is equal to m. Okay, so let's look at number 58. We have log base 7 of x plus 2 equals -2. So we change it into an exponential expression. 7 to the -2 is equal to x plus 2. Okay. 7 to the -2 is the same as 1 over 7 squared. And all we're doing at this point now is solving for x. And I want a nice answer. I'm not using my calculator, okay? 1 all over 7 squared is 49 equals x plus 2. And then isolate x. So x is equal to 1 over 49 minus 98 over 49. That's the same as 2. So x will equal -97 over 49. So we have to check that, right? Yeah. So zip over here and do our check work. And when you do your check, you're putting it into the original expression. So we'll have log base 7 negative 97/49 plus 2. And on the other side, we have negative 2. When you do these checks, you cannot be moving stuff around. You're keeping it separated, okay? So thou shalt not cross this asymptote, so to speak. So I simplify this side, and I'm comparing it to this side. Sometimes you have to simplify this side too. Okay, in this case, you don't. So I'm just literally working on this side and then making sure it is negative 2. Okay, so let's do it. Log base 7 of this thing is negative 97/49 plus 98/49. On the other side, we have negative 2. Then I have log base 7 of 1/49. The other side, negative 2. And of course, this is log base 7 of 1/7 squared. The other side, negative 2. And then we could rewrite this log base 7 of 7 to the negative 2. And then, of course, log base 7 of 7 to the negative 2 is just negative 2. Okay. And we ended up with a true statement, so I can walk back over here and officially give it my stamp of approval. And there's my answer. Okay. Okay. Let's look at another. So here's 66. I have the ln of the square root of x plus 4 equals 1. And again, use the definition of logs. In this case, it's of course ln is log base e. So the square root of x plus 4 equals 1. So I say e to the 1, e is equal to the square root of x plus 4. Okay. Then I have a radical equation. So I need to square both sides. E squared is equal to x plus 4. And then solve for x. So x is e squared minus 4. Okay, so check. Go back to the original equation. So I have ln, and I'm plugging in e squared minus 4 for x. It's 4. And then again, don't be messing around with either side. You keep them separated. Okay? Don't mess around. So ln of the square root of e squared, 4 minus 4 is 0. And then this is the ln of e squared to the 1/2. I just rewrote the square root as a rational exponent. And then you could use our exponent rules. So remember, if you have a to the x raised to the y, you get a to the xy. So e to the 2 raised to the 1/2 is ln of e to the 2 times 1/2, which is 1. And then, of course, the ln of e is just 1. We got 1 equals 1, so we can come over here and give it the stamp of approval. Okay. Using some of the properties of logs here in 72, I have log base 4 of x plus 2 minus log base 4 of x minus 1 equals 1. Okay, so in this problem we want to, again, take advantage of the definition of logs, but it's not set up for it yet. So you need to condense using the properties of logs. So you can rewrite this using the quotient rule. You'll have log base 4 of x plus 2 all over x minus 1 equals 1. And then use the definition. So 4 to the first power, which is of course 4, equals x plus 2 over x minus 1. And we're going to multiply both sides by x minus 1 to clear out the denominator in the rational expression. Yeah. Okay. Okay. So I'll distribute here. I get 4x minus 4. On the other side, the x minus 1s go away, and you get x plus 2. Move the x over, you get 3x. Move the 4 over, you get 6. And then finally, we're getting x is 2. Okay, we're not done. I need to go back to the original equation and check it. So not here, here. Okay, before you did any sort of manipulations, that's where you have to go. Okay, so log base 4 of 2 plus 2 minus log base 4 of 2 minus 1. And again, do not cross the asymptote. It's more of a comparison here than anything else. So here we have log base 4 of 4 minus log base 4 of 1. This side we have 1. Log base 4 of 4, so 4 to what power is equal to 4? 1. And then 4 to what power is equal to 1? 0. So I still have 1. 1 minus 0 is 1. That certainly is equal to 1, so therefore it worked. Stamp of approval. Move on to the next problem. Okay, so this time, let's get a piece of paper. Here we're looking at problem 70, and we have log base 6 of x plus 3 plus log base 6 of x plus 4, and that all equals 1. All right, so we want, again, to apply the properties of log, so we're going to condense this. So you'll have log base 6 of x plus 3 times x plus 4. Over here, 1. Use the definition, so 6 to the first power is equal to x plus 3 times x plus 4. So 6 is equal to x squared plus 3x plus 4x is 7x plus 12. Set it equal to 0, it's quadratic. So x squared plus 7x plus 6 is 0. And then factor it. So you get x plus 1 and then x plus 6. And so we have two solutions, two potential solutions. X equals -1 or x is -6. Okay, so let's do our check work now. I'm going back to the original equation. So I have log base 6, -1 plus 3, plus log base 6. And I'm checking each x value separately. So first I'm checking -1. Okay, so log base 6 of -1 plus 4. And I want to compare that to 1. So I'll have log base 6 of 2 plus log base 6 of 3 is 1. I can use the properties of logs here. 2 is greater than 0, 3 is greater than 0. It's legal. So log base 6 of 6 equals 1. 6 to what power is 6? Well, that's equal to 1. 1 equals 1, it gets the stamp of approval. Okay? Let's try x is -6 now. So plug this in, you get log base 6 of -6 plus 3 plus log base 6 of -6 plus 4 is 1. So now I have log base 6 of -3 plus log base 6 of -2 is 1. This is a huge problem now. You cannot have negatives inside of logs. So as soon as you see this, it's dead. This is not a solution, and we can sort of kick it out of our solution set, and we're just left with x equal to -1. Okay? So here our conclusion is x cannot be -6. Okay, the last method for solving then here, I guess we'll label this part B, using the one-to-one property. So again, in general, if the function is 1-to-1 and you have f of x1 equaling f of x2, it forces x1 to be the same as x2. Otherwise, you would have failure of the horizontal line test. Okay? So in the context of logs, how does that look? If log of x1 is equal to the log of x2, then because it's 1-to-1, we will have that x1 is equal to x2. Okay, so that's the property we're exploiting. Okay, so 84 then, let's take a look. we have log of x plus 7 minus log of 3 equals log of 7x plus 1. Okay. So first I'm going to combine these. I want to get log of something equals log of something. Okay, so I'm going to combine these. I get log of x plus 7 all over 3 equals log of 7x plus 1. Okay. Then you can use the one-to-one property to equate the guts on either log. So x plus 7 over 3 equals 7x plus 1. Okay. I'm going to multiply both sides by 3 to get rid of this denominator. So I'll have x plus 7 equals 21x plus 3. And then I'm going to, thank you. I'm going to get the x on this side, so 7 is equal to 20x plus 3, and then I'm going to 3 over there. So you get 20x is 4, and then I'm going to simplify. So 20x is 4, so you get 4 over 20, which is, of course, 2 over 10, which is, of course, 1 over 5. Okay, so I ran a room there. We still need to check this in the original logarithmic equation. So let's go ahead and do that. I need a little room here. So the check of x is 1/5. So I'm plugging it into the original expression. I have 1/5 plus 7 minus log of 3 equals log of 7 times 1/5 plus 1. Okay. So over here I have log of 1/5 plus 35/5 will be 36/5. And then minus log of 3. Over here I have log of 7/5 plus 5/5, which would be 12/5. And then you could use your quotient rules. Both of these are positive real numbers, so we can apply the laws. So you have 36/5 divided by 3, which is the same as multiplying by 1/3. The other side, log of 12/5. Here then, log of 3 goes into 36 12 times, so 12/5. Over here, log of 12/5. And so using the one-to-one property, 12/5 is equal to 12/5, and we're done. It works. Okay. So you come back here and give it your stamp of approval and move on with life. Okay. Okay. So lastly, let's kind of look at an application. So 104, we have a formula given for the population. I think it's people in millions and the number of years after 2010. 25.1 e to the 0.0187 t. Okay. A is a population millions. And then t is going to be the number of years after 2010. Okay. Okay, so first off, they want to know what the population is in the year 2010. So that's a simple plug and chug. It will be A equals 25.1 e to the 0.0187 times 0. Right? And we could even do this in our head. This will be 0, this entire exponent, so it'll be e to the 0, which is 1. So you have to put 25.1 million people. So at time 0, the population is just this coefficient. Then they want to know, when is the population be 28 million? So in this case, we're going to have to solve for the t in the original equation. So you want a to be 28 million. Here we'll have 25.1 e to the 0.0187 t, and we want to solve for t. Okay, so again, you need to isolate the exponential term before you can do anything. So you'll have e to the 0.0187 equals 28 divided by 25.1. You can take natural log on both sides. So ln of e to the 0.0187 t, I forgot my t there, equals ln of 28 divided by 25.1. ln and this e will cancel each other out, just leaving you with 0.0187 t. Over here, ln of 28 over 25.1. Finally, divide by this constant here, so you get t is ln of 28 divided by 25.1 divided by 0.0187. And if you put it in your calculator, you'll get approximately 5. So the population will hit 28 million. In the year 2015. It's 5 years after 2010. Okay, so that's 3.4.